My name is Sam Cooper. I'm an Associate Professor of AI for Materials Design at Imperial College London. This evening you've heard two wonderful talks from my colleagues Aaron and Mona, explaining how AI is helping us explore the chemical space and find the best compositions for next generation batteries, and also to predict and control devices at the macro scale. But in between these two length scales is something just as important, but far less understood, and that's microstructure. Microstructure is the internal structure of materials at the micro scale. Think pores and particles, phases and interfaces in the range of 10 nanometers up to 100 microns. Unlike atoms, we don't have the nice clean equations that allow us to predict the structures that will emerge. And unlike devices, we aren't able to directly specify the shape and arrangement of the components inside it. Instead, they emerge indirectly from the processes that manufacture them. To explain to you why microstructure is so important, I'm going to have to do a quick reminder about how lithium-ion batteries work. So here you've got a nice cartoon of the cell, and this image would be about 1/4 of a millimeter across inside a real battery. So you've got particles of anode material in black and cathode material in white. And here's a little lithium ion that's going to travel to the surface of a particle, wiggle through the pore network, and arrive at the surface of a particle on the opposite electrode, and that's what gives you the power. But it's not just one lithium ion doing this. In fact, in this image, it would be about 1 trillion lithium ions all competing at the same time, pushing each other out the way, navigating these tortuous pathways. So if we can improve the shape of the pore network, we can improve the performance of the cell, and this will allow you to charge up your car much faster and drive further. So if we want to improve this microstructure, we're going to have to understand how to make it. And this is typically 4 steps, or can be summarized as 4 steps. First, you've got mixing, where we put solids that are the active material, the binder, the additives, as well as a liquid, which is a solvent, all into a mixer and mix them very vigorously together. The next step, we take this ink and coat it very finely on a metallic foil. Then we pass that foil into a drying oven and the solvents evaporate off. And finally, we pass this coated foil through giant metal rollers that crush down what remains to make it denser. There is so much physics going on in these 4 processes. You've got solids, liquids, gases, you've got fluid flow, you've got evaporation and phase change, and you've got fracture and deformation. So complicated. And what comes out the end of this process is as complicated as you might expect. You can see here a scanning electron microscopy image of the cross-section of a typical lithium-ion battery cathode material. The big gray blobs are the active material, and in between them you can see a complicated network of pores and a carbon binder domain. However, the state of the art for physics-based modeling of these structures looks a little bit like this. And the reason is exactly what I told you. The physics is too complicated. It's too expensive to compute. So the best we can really do today is to drop idealized spheres into a perfect box and hope that the arrangement tells us something about the possible behavior. I'm going to explain to you today 4 ways in which AI is helping us do better than what I've just showed you. We've got characterization, generation, design, and validation. Firstly, characterization. Let's go back to our SEM image. Once we've captured this image with our microscope, we now want to go to every single pixel in the image and allocate it to a particular material. Is it active material? Is it pore? As you can imagine, that's an extremely arduous task. However, there have been massive advances in computer vision in the last 5 years. This is Dino V2 from a company called Meta that I'm sure you're all familiar with, and it's a vision transformer model. And this model has been shown billions of what we call natural images. And during its training, the job was you pass it an image and you cover up patches and ask it to paint in the missing patches with what it thinks should be there, just as you could imagine a human would do. It turns out if you train it to do this with a vast amount of data and you have a sufficiently complex model, the model builds an internal representation of the world to make sense of what's going on and make sensible predictions about what was missing. So you can see in the rainbow image, which is a representation of the same kind of vectors that Aaron was talking about, that it has some kind of intrinsic understanding of the difference between dogs' legs, which are both green, and a dog's ear, which is orange. We can take these models and apply them almost unmodified to our microstructural image data. And you can see I've now got some kind of rich description at each point in space that characterizes each pixel in the context of every other pixel in the image. I can then take those vectors and pass them to a classifier in combination with a bit of human expertise and generate a very accurate and very fast map of the distribution of phases inside my material. The next thing that AI is helping with, generation. Let's go back to our beautiful SEM image. We've segmented it, we have a very clear map of what's going on. However, there's a problem. Many of the things that we need to know about lithium-ion batteries are actually intrinsically three-dimensional in nature. This means that the 2D image, in a sense, is not good enough. We need to understand the distribution of particle sizes, the connection of interfaces, the tortuosity of pore networks, and the electronic transport through the solids. These are 3D concepts. However, 4 years ago, a brilliant student of mine, Steve Kench, discovered a method using generative AI to generate 3D structures from a single 2D image. This means that you can speed up your characterization workflows by a factor of 100 and extract all the complicated battery-relevant metrics from a single two-dimensional image. The next stop is design. So far, I've showed you that we can generate three-dimensional microstructural data from a single 2D image. But what if we, instead of showing our model just a single image, we showed it images from a range of different materials manufactured using distinct manufacturing parameters? Once we've trained this model, which can be done on the order of a day on a GPU, a graphical processing unit, we can then use this model to swim around the space of all possible manufacturable electrodes. This allows us to then build it into what we call an optimization loop and search for the manufacturing parameters that leads to the microstructure that leads to the battery performance that we're looking for. This, 2 years ago, led to the spin-out of a company from Imperial College, where I am the chief scientist, along with Steve and my other brilliant student, Dr. Isaac Squires. And the wonderful thing is, of course, microstructure is not just important for batteries, it's everywhere. Microstructure is in the pharmaceuticals, and it modifies the way that the drugs dissolve in your system, in the surfaces of advanced alloys where the crystal structure changes the toughness, and in the arrangement of active particles inside a catalyst that modifies the activity by orders of magnitude by changing the active surface area. The final stop on our tour of AI for microstructure is about validation. In recent years, there's been a huge push for robotic labs, and this is for a range of reasons. One of them is that robots don't get bored. They are very happy to do the same task over and over again, and even the most diligent, conscientious PhD student, after they've assembled their 100th coin cell, might be feeling a bit tired of the task. But more than that, they are good at these repetitive tasks, and so when you assemble a coin cell, you have to put a piece in and then stack another piece exactly on top, and then another piece exactly on top of that, and if they are misaligned, your performance will not be what you expected. The robot is very good at that task. It doesn't have clumsy fingers, it has suction cups and little lifters. But even more than this, the robot does not get bored of the side tasks. At every single stage in this process, the robot will take the cell and weigh it and take a photograph of it and save that data in the right place. A human could do that, but it's an awful lot to ask. So how can AI help us here? Well, as Aaron highlighted earlier, there's been massive advances in agentic AI, and I've got two fantastic students here tonight, Felix and Shears, who are developing agentic models for controlling labs. These models can, by having read all of the literature, design pathways for experimental workflows in these robotic labs so they can react in real time as the data emerges, making sensible decisions about where to look next. So, I hope I have shown you that microstructure is very important. Atoms help us understand what is possible. The devices help us understand what's necessary, but the microstructure is what's telling you what's actually going to happen. And with AI, this missing layer is going to be something that becomes visible, designable, and controllable. Thank you.